Hello, my name is Paweł Honzinski, and I'm a Senior Marketing Manager at Aras Corporation. Thank you for joining me during this virtual session. I will be discussing a synergistic relationship between PLM platforms and simulation, where the value of the whole is much more than the parts. Please note that this is not strictly an academic paper, but a discussion of use cases surrounding integration of simulation with PLM platform. The reason we are talking about this is an incredible explosion in complexity of things that we design. Way back, most of the products were simpler. The focus was typically on a single domain as a design silo, mechanical CAD and electronic schematic, software code. Then, somewhere along the line, we introduced the next level of complexity because now we had to worry about the interactions between mechanical, electronic, software, although in a rather straightforward way. And typically, no more than two domains were intersecting at a time. Mechatronic became a big word. Today, we worry about systems in the true sense of the word. The system of interest interacting with other systems of interest, and all in the context of the overall system of systems. Autonomous vehicles being a case in point. System context plays a huge role in the rise of complexity. Things talking to each other over networks, over-the-air software updates, information-driven maintenance, and it is only accelerating. With the initial levels of complexity, the focus was primarily on the product. PDM, PLM systems manage products' bill of materials BOM with little understanding of the design intent, variability, multidisciplinary dependency, or even traceability to the requirements. With the digital transformation, we tried to change that. But simply moving the current tools, silos, and best practices into the digital world without changing the overall context is not going to suffice. To begin this journey of digital transformation, companies are moving their focus from products to systems and to system of systems. The product itself is a system expressed as a multiplicity of interrelated abstractions and domains that all interact together. Your reality, however, consists of many other related systems that must be considered together. For example, the system context, manufacturing systems, maintenance systems, and so on. That system of systems interaction is a major contributor to the overall complexity. This entire set of systems needs to be analyzed as a system of systems because they all interact. They must be considered simultaneously to optimize the overall performance and to identify and mitigate undesirable emergent properties between the system boundaries. Without the system of systems view, the whole design process slows down and the final product is not optimal for its intended market. It often does not meet all the requirements, and if it does, it is most likely over-designed. The system of systems view is at the core of systems thinking, and it is nothing new to the systems engineering community. What is new is the realization that with digital transformation, all this must be somehow accounted for in a digital thread that the entire enterprise will benefit from. And that it goes well beyond MBSE, model-based systems engineering, which primarily focuses on the left side of the engineering V-curve. Dealing with this holistic system of systems view of your product requires digital thread, which in turn requires a PLM platform capable of managing the entire system lifecycle from concept to disposal. A digital thread that reflects your realities. When we are confronted with designing a complex system, the immediate reaction is to divide and conquer, which is the core of reductionism. Systems to subsystems, to parts, or to functional decomposition. In fact, Focusing on implementation domains as separate and disconnected activities, mechanical, electronic, software, is a form of reductionism as well. Wrapping one's mind around the whole system is often too complex without the right abstractions and is the special expertise of the systems engineers on the team. Systems engineers do a lot of systems thinking that fails to float down. While responsibilities and tasks do float down, requirements and a deep understanding of the system behavior do not. We put blinders on the engineers working on the subcomponents of the system. So what's lost with singular focus on reductionism? A true understanding of the overall system, dealing with system trade-offs, understanding and leveraging emergent system behaviors and properties, optimizing the overall system, and so much more. Let me be clear. I'm not saying that systems thinking is a replacement for reductionist design practices. These are complementary approaches that should be applied simultaneously and continuously when designing and analyzing a complex system. These approaches can be used at any level of the system design and in any domain. We believe that systems thinking and reductionism are completely complementary approaches. As I already mentioned, a balanced approach requires a PLM platform capable of managing the entire system lifecycle from concept to disposal, a digital thread that reflects your realities. The agility of the system development process depends on the ability to continuously and rapidly answer the question, how good is my system design? This process is agile and iterative and can start at any level of completeness of the design and at any juncture of the engineering V-curve. The explore and validate process is heavily reliant on simulation. This requires the right tools, proper level of automation, access to the right set of design data at any level of system abstraction and at any intersection of the subsystems. And of course, an ability to retain a system of record, what was done, when, by whom, with what tools, with what data, with what results. This cannot be achieved when simulation is a silo and when the design data is not easily traceable. In other words, this can't be achieved without simulation being part of the digital thread. This also requires validated simulation models that are automated, highlighting the need for good simulation governance practices across the enterprise. Keep in mind that you can always be agile, but you need to be moving forward, not sideways or backwards. To rapidly and incrementally move design forward, the team needs the right platform and tools for continuous design exploration and validation. Assuming system architecture, part of the MBSE representation, is at the core of your design, you need a PLM platform to capture the related data and metadata for traceability via a digital thread. This is important because system architecture is the connective tissue for all other system representations and implementation details. This PLM platform must support configuration management and variant management throughout the lifecycle. Lifecycle that starts with the basic concepts of what the system is supposed to do and extends all the way to system disposal. The PLM platform must also be open, extendable, and easily customizable, as no digital threads are alike. Your digital thread must reflect unique particulars of your enterprise, and it will continue to change and evolve over time. This highlights the need to go beyond the traditional product-centric PDM-PLM systems towards PLM platforms. Unlike PDM-PLM systems, PLM platforms capture and reuse both the content and the intent of system design. Exploratory greenfield simulation is a good example of the design intent that is often external to the PLM and therefore not included in the digital thread. On-demand, pervasive simulation management supports continuous system exploration and validation a process required to identify, investigate, and mitigate emergent system properties and behaviors. I just mentioned that system architecture is the connective tissue for the entire system, and therefore it needs to be represented in a digital thread. But what does that mean? System modeling tools used by system engineers, example Cameo or Rhapsody, generate highly complex data structures. These tools operate on details that go way beyond what digital thread needs and use data models that are not compatible with each other, tool to tool. And yet, digital thread needs to capture some of that data from multiplicity of MBSE tools in a tool-agnostic form. The most reasonable solution is to define which system architecture elements authored in these models are key to defining your digital thread, and then focus on synchronization or federation of only those elements between the authoring tools and the digital thread. We call these elements anchor items. The benefits are clear. There is a single system architecture for all, the connective tissue, and the digital thread remains tool agnostic and extendable into the future. The mapping between various MBSE tools, high granular views, to a single digital thread, low granular view, is the Rosetta Stone of the digital thread. While the need for digital transformation is well understood, the execution is driven by the specific needs and priorities of the enterprise. This includes approach to the digital thread. I already mentioned a few times that it is always your custom digital thread, since there is no such thing as a digital thread out of the box. And it is often a partial digital thread when you embark on that journey. The key is to ensure that there is something in each part that allows to later. Notice that in that digital thread definition, we include what happens to the assets in the field after they are manufactured. Very important. For example, one of our automotive customers is currently building two partial digital threads in two divisions for two purposes. Model-based development is doing engineering data management, while a different group is doing vehicle performance management that involves simulation. These digital thread segments are still disconnected, but both use the same exact tool-agnostic system architecture model. In that sense, they are joined at the hip through that common representation of the system architecture, even if they are not yet used together. Regardless of where or how many of the partial digital threads are created, it is critical to view the system architecture as the core foundational data structure on which to hang the rest of the data. System architecture is the connective tissue of the digital thread, and both form a unifying umbrella providing context to the rest of the system. And therefore, it is imperative that a PLM platform can model and manage that system architecture in a tool-agnostic way. The following is an outline of the digital thread I just mentioned, the one that is being implemented at an automotive company. This is a 100% customer's view of what digital thread needs to connect now, and to expand it along the V-curve in the next phase of the project. Using Aras Platform, the company has implemented a data modeling framework that allows them to customize their systems and engineering data across 3 connected layers within the digital thread. That is what you will see during the demo video. The systems engineering team manage the system architecture. The engineering teams create and validate the maturity of the tool-independent engineering data. This becomes your single source of truth, with the system architecture model serving as a connective tissue. Simultaneously, product variant data is added to the system at the appropriate points, ensuring that you consistently maintain a 150% system. When the need arises to extract a single product variant, a 100% system, the 150% system is resolved based on the variability rules. In addition, custom mapping rules are applied to further specialize the data for simulation. Simulation models are automatically extracted and presented to the simulation process, which can be run locally or in the cloud. The results are recorded and verified against the original requirements, which include parameters expressing targets as real values. Let's see what this looks like in the software. The diagram shows flow of the demo, although some steps were cut out in the interest of time. The demo is presented and narrated by Malcolm Pantaki, Aras Vice President, Analysis Solutions. Let's see it.
So here, what you see listed is a tree of versions of the system AC32A V01E. These are the system specifications we've spoken about. So let's look at the system hierarchies for this particular system to understand the history of changes and the content of these systems with their associated engineering data containers. What you're seeing here is a visual view, a certain snippet of the digital thread. Things are appropriately color-coded. All of this is configurable. This is a low-code environment. Through configuration, you can set up whatever you wish to in terms of views. The red connections here indicate versions. So you see the first version here, the 1.1, 1.2, etc. You can create an entire tree of those versions. The blue lines indicate containment. So for example, here you have version 1.5. It consists of these subsystems. And then the front axle, for example, consists of these subsystems here. So that's your full view. But these are live. All of these are live. So I can, for example, say, let's take a look at version 1.5 of this system. So here's some high-level metadata associated with it. It indicates that it is a part of a tree, tells you what the parent is within the tree, other metadata associated with it. And then you also have the detailed information down below. So here's the structure of the system, but then you have other data here. What you're seeing, for example, are some variant points where the variability information has been added. And that's key because you want to add and apply variability to your data structures right from the start so that they evolve as your data or system definitions evolve. And then associated with each of these systems, you also see the EDCs, or the engineering data containers. The way to deal with variability is through this module here that allows you to pick features and options and then simply resolve them. And then you get the resolve structure that can be used downstream by various stakeholders for various purposes, such as simulation. So let's take a look at one of these engineering data containers. Once again, this is a data structure that is completely configurable. We believe that each of our customers needs to configure their engineering data the way they need to. So this data structure, the the EDC for front suspension, consists of a large number of underlying data. But it's difficult to edit the object this way. So here's the GUI that was created to quickly and easily view all of this data. Here are some hard points or locations. Down below, you've got masses and inertias of the subsystems. Within this GUI, multiple engineers can be editing these things simultaneously. Teams of engineers can work, confirm the data, confirm the maturity of the information simultaneously while not stepping on each other's toes. With multiple versions of these complex systems and EDCs across various vehicle projects, it's important to be able to easily find and compare data. So here's what these visual queries might look like. Here are a couple of them. So here's a very simple one. It simply says, go find me the EDC bodies that belong to systems that have the following property, that have one E in their names. When you run the query, you get a set of bodies that meet that criteria. Very simple query, easily creatable, easily editable. Here's a slightly more interesting one. In this query, you're looking for front suspensions that belong to certain systems. And these are all the criteria that those systems need to meet. They need to have in their name V01E. They need to contain bodies whose mass is greater than 755 kilograms and wheels whose tire radius are greater than 170 millimeters. Now, this is the kind of query that's really easy to create. It wouldn't take more than about 2 minutes to create a query like this, and then you can always edit and run them. And when you run this query in the current database, these are the front suspensions that meet those criteria. So it's really easy to find information in this very complex web of data with lots of systems, lots of projects, lots of products, all stored in the same environment. Then I can pick a couple of these results, for example, and compare simply by right-clicking and comparing, and then you'd see something like this. I'm comparing, in this case, two versions of that front suspension. This indicates to me that there are differences. Look in further and you'll see all the data that's the same, and then the data that are different are clearly marked. It's an easy graphical way to not only search, but also to compare these very complex data as you're working with it, reviewing it, and editing it. Now let's take a look at where the engineering teams can go from this definition of a system and its EDCs to a graphical view of the complex digital thread for a given system that might include simulations that are performed on it with simulation results, ultimately then compared to requirements. So let's review the systems. These are some top-level systems in the database here. Let's take a look at the AM54 vehicle. So here it is, some simple top-level metadata associated with the system. Down below, you have all the relationships. So here is the basic system structure that contains requirements, documents, and requirements, the functional specification of that system, and then the logical or system element breakdown of that system. So the requirements might look like this. Here are a set of requirements associated with it. You see only 3 over here. You could have hundreds of them or more. Here's the functional structure. Here's a tree of functions that define the operation of the system, and then the system element structure. Now this kind of view is fine, and there's a place for it. But what's really interesting is the graph view that you can get of the actual digital thread, and it's live. You can work with it and access data directly from here. So here you see the system we just looked at with its requirements, functional specifications, and system element specification. Extend the requirements, and you get the 3 requirements here. There's a force that needs to be less than 20,000 newtons, maximum force here at different locations, less than 10,000 newtons, and a stress requirement. If I take a look at the functional breakdown, here's what that looks like. So here's the first level of the functional breakdown, and then further levels down below. Once you have a functional breakdown, you usually want to connect that or have these functions be implemented by certain system elements. So let's take a look at the system elements in this vehicle. So you can see a bunch of them. It is a system of systems that captures the atmosphere, the rest of the world, the road, the driver, and then the car itself, or the chassis, as they call it. As I mentioned, this was a Modelica model that was imported into the platform. Open up the chassis. It has a whole bunch of subsystems over here. So back down to the functional view. So I could, for example, figure out what implements this body stiffness and strength function. Or what deals with the torque and application wheel. So these are fully connected data structures. Now let's take a look at what one can do with the system specification. So here I've got a representation of the overall vehicle, the Modelica model that was imported. If I open that up, I see simulations. And then when I look further down there, I can see the simulation results for a particular simulation. This was a system simulation followed by 3D CAD simulations. Here are the results from a number of them. And if I take a look at this, it's green. There's a connection back all the way to the requirement here. Here's another result connected to a second requirement. from the system simulation, and then a third result here from the 3D CAD simulation, showing that this particular version of the CAD and the design meets all the requirements. This graphical digital thread view is extremely valuable and powerful as you navigate through this complex web of data, showing data going from the top level system to functions, system elements, requirements, simulations, trees of simulations, and then connected back to requirements.
I hope you enjoyed this short video since it did touch on many subjects that I was discussing. Unfortunately, not all system data is accessible for inclusion in a digital thread. Silos are enemy number one, and there are no more divisive silos than those between the different major disciplines when building a digital thread for the entire system model. Workarounds create direct domain-to-domain integrations, but that is not an efficient way because it creates a lasting dependency on those specific tools. Since PLM platforms are where digital threads are created and managed, these platforms should have the ability to connect these domains via the central system architecture model managed by the PLM platform. We know that mechanical structures are already part of PLM space, but what about electronics and software? Let's take a quick look at that chart. Many organizations manage printed circuit board assemblies on their PLM systems, but only as a BOM of materials and components that constitute the physical board. That BOM helps to manage the manufacturing and assembly process, but is of little benefit to the digital thread of the overall design of the system. What would be much more beneficial is the schematic representation of these designs, since that is where the target performance, device functions, pin assignments, and interconnect networks are defined. What is truly fascinating is that these schematics are in fact very similar to the system architecture models, the only difference being the hierarchy of the abstraction layers. In other words, the lowest layer of a system architecture that is mapped to implementation in electronics is, in fact, the highest level of abstraction in the schematic of that electronic design. Having that relationship firmly defined in a PLM platform would instantly make electronics designs available to the system optimization in the true sense of systems thinking. For example, timing budgets established in the system requirements could be simulated, verified, or optimized within the schematic via traceability between system architecture and the electronic schematic, taking a holistic view of the system. But for now, that is not possible because vendors are not enabling it, while users are still focused on the more fundamental aspects of a digital thread. Electronic design remains in its own silo and therefore cannot be included in a digital thread from the systems thinking perspective. Similar situation exists with embedded software. Just like electronics data, ALM data is a silo that remains disconnected from the PLM platform and the overall system digital thread. I'm mentioning this since software is such a critical part of a system, obviously, a role that is only destined to grow exponentially. The challenge is not to shift the entire LMM process into PLM. The challenge is to make PLM aware of what software does and how that fits in the overall system design as a traceable via the system architecture. This graphic shows a very high level of the type of relationships that could be considered. Software remains in its own silo and therefore cannot be included in the digital thread from the systems thinking perspective. In the end, it's you who needs to justify your use case of investing in incorporation of system model and simulation in PLM platform based on your digital transformation needs. You then need to define just what this means to you, which sections of the digital thread, what anchor items, etc. You need to make simulation a fundamental part of this process, not just from the simulation perspective, but more importantly, from the systems thinking perspective. And finally, silos are your enemy, especially silos defined by the specifics of the authoring tools and data models used by these tools. Again, my name is Paweł Honzinski, and I'd like to thank you for attending this presentation. Goodbye.